Well, we are going to talk today about complex numbers in their trigonometric form. So I'm sure you're thinking, how could complex numbers get any more fun, Sarah? And I'll tell you right now, if we involve trig. So remember what a complex number is. A complex number is of the form a plus bi, right? We learned that before, where of course we know that I is the square root of -1. So complex numbers encase all of the reals and the non-reals, also the pure imaginary numbers. If I want a real number, I just let b be 0. If I want a pure imaginary number, a is 0. Anything with an I in it is a non-real number, okay? So we can actually graph these. So a graphical representation, that sounds really fancy, representation. So the graphical representation of complex number, we can actually think about so think of a real number, right? A real number, if I asked you to graph the number 2 on the real number line, you would come over to 2 and there, that would be your number 2. So we kind of have the same idea here, except notice a complex number has 2 parts to the number. So the way we represent this graphically is we take a page from Descartes, right, the Cartesian coordinate system, and we say, well, remember, the Cartesian coordinate system, you guys, is really just a real number line put horizontally and a real number line put vertically. That's all a Cartesian coordinate system really is. So when we look at a graphical representation for a complex number, what I'm going to do is I'm going to have a real number line horizontally. So we say that this is the real axis. And then what we actually do is we say, okay, then I'm going to let the y-axis be the imaginary axis. It does exist. I know that's complex, haha. I know that's a little bit weird, but it's an imaginary axis that actually does exist. And basically what this graphical representation does for us is it just gives us a way to kind of look at, you know, the magnitude of the real part of my complex number and the imaginary part of my complex number. So for example, I'm just going to graph a couple of these and then kind of call it good because there's not a whole lot to explain here. But if I had the point, you know, 1 plus 3i. So what is the real part of my number? The real part of my number is 1. What is the imaginary part of my number? It's 3i. So to graph this in the real direction, I'm going to go over 1. In the imaginary direction, I have basically a magnitude of 3. So this right here would be the number in a graphical representation, 1 plus 3i. Likewise, if I had something like 4 minus 2i, right? What is the real part of the number? The real part of the number is 4. The imaginary part is -2, right? Because of that negative right there. So I'm going to go to the right 4 and down 2, and that's my number right there. So pretty straightforward, I think. Notice if I had the number, let's say I had the number 7. Well, actually, let's say I had the number -5. So -5 is all a real number, right? We don't actually have any imaginary part to it. So you think of -5 as, well, we don't think of it that often, but we can think of a real number as a complex number if we think of this as -5 plus 0i. So where would I be? I'd be at -5, 1, 2, 3, 4, 5. And then I would go nowhere up and down, right? Because it's just a real number. So this makes sense that a real number should just lie on the real, I don't know, whatever, I'm not an English teacher. It should lie on the real axis, right? And not have any imaginary part to it. So this is kind of a cool way that we can represent these numbers. Now, what you're probably asking, actually, I know you're probably not, but you're probably asking, but Sarah, in the real numbers, we talked about something like absolute values. So when we talked about the absolute value of 2, right, we said that that was 2 because that is the distance that 2 is away from 0. If I looked at the absolute value of a -3, right, what's the absolute value of -3? It would just be 3 because -3's distance from 0 is 3. So you're probably wondering, and I'm sure you are, is how do we define absolute value when it comes to a complex number? Well, I'm going to tell you whether you want me to or not. Let's just say we have an arbitrary complex number out here. So I know I gave, I indicated what we have here, but without lots of generality, let's just say we have an arbitrary complex number in the first quadrant we'll call this a plus bi. So remember, absolute value is distance from 0. So that is exactly what we're going to define an absolute value of a complex number to be, is now that we have a graphical representation for it, right, which we had for real numbers, now we want to do this for complex numbers. What do you guess the definition of the absolute value of a complex number would be? That's right. I can hear you say it right now. It would be the distance from 0. And what is 0 in this case, right? 0, which is equal to 0 plus 0i, that would just be the origin. So if I want to know the distance that this complex number is from 0, I want to know the distance this number is from the origin. So if I look at this, remember, we're just at some a. I'm not actually at whatever this is, like 3.5, right? So if this distance right here must be a, because that's the real part of my number. This distance right here must be b, because that's the imaginary part of my number. So how do I find the absolute value of a? This is what I want here. I want the distance of the hypotenuse right here. And we know how to do that, right? I mean, our good buddy Pythagoras has been giving us lots of wonderful, well, he or his brotherhood, right? Have been giving us a lot of use of the Pythagorean theorem. And so right now we can actually define what it means to take absolute value. Okay, so this is a kind of a definition. So how do I find the absolute value of a plus bi? I'm sorry, there's a brick. Whoever designed that was ridiculous. I'm sure you heard that. There's a hallway by my office that has a brick floor. So anytime anyone has a cart or anything, yeah, that's what happens. So, all right, look at what I have then. I have this right triangle, right, where this distance is a, this distance is b. If I wanted to find this absolute value, let's just call that c. We have a squared plus b squared equals c squared. I'm going to square root both sides, taking the positive root because we're talking about a distance. So what is this distance here, that absolute value? It's just the square root of a squared plus b squared. Pretty easy, right? Not too bad. So we can do some examples with this if we want. So we'll just do, this isn't too bad, so I'm going to probably just do one quick example. So let's graph the number -3 minus 5i and find its absolute value. Okay, so this isn't going to be too bad. So I'm going to graph this, and you'd, well, it's not going to be too bad if I know how to spell, which I usually don't. All right, so I know this guy's in the third quadrant, right? Because it has a negative real part and a negative imaginary part. 1, 2, 3, 4, 5. So this number is right about here. There's my number, -3 minus 5. I know it's weird now to say, remember, this is my real axis, this is my imaginary axis. So I have graphed the number -3 plus 5i. And if you think about, you don't always have to memorize things, right? We know that this is -3, this is -5. So how do I find the absolute value right here? I'm just going to use the Pythagorean theorem. So the absolute value of 3 minus 5i is going to be the square root of, parentheses are important, -3 squared plus -5 squared. I don't know how many times I wrote that on my calculus test that I gave the other day. Parentheses are important. Parentheses mean something, people. 9 plus 25. So what is the absolute value? What is that distance from that number to 0? Looks like it's the square root of 34, which I don't think we can simplify, right? But if we wanted, you know, distances, sometimes I would argue is a good time to give an approximation. I mean, go to Home Depot and tell them you need square root of 34 feet of whatever you need, right? and like I get often strange looks at Home Depot. All right, so that should be pretty easy. I hope that makes sense. That's how we find that absolute value. So why is this in a trigonometry class? Because people, we started drawing right triangles. And if we're going to start drawing right triangles, right, then the mathematicians in their weird little brains, not weird, in their interesting little brains, start thinking trigs. So now this is the meat of this lecture, trigonometric form. All right, so I'm gonna grab a complex number, I'm going to put it in the first quadrant, so without loss of generality, which means I could just as easily put this in the second quadrant, right? Or the third or the fourth, it doesn't matter. And so this is going to be the number a plus bi. Okay, so here's some things that that we know. So I'm going to define a couple things here. So if I kind of make my right triangle, I'm going to call its absolute value r, okay, because we're used to that when we talk about trig. I know that this distance here must be a because that's the real part of my number, and I know that this distance here must be b. And just because it looks like we have a right triangle, of course, I'm going to define this right here to be theta. So you can kind of see where this is going, right? So I have some relationships here. So if I take the cosine of theta, notice that the cosine of theta, right, is that real part of my number divided by r, which I know, remember, r is the absolute value of that number. So I have a over r, or if I wanted to rewrite this, which, what do you know, I do want to, this is a equals r times the cosine of theta. Also, I could, if I look at the relationship with sine, what is sine? Sine is b over r, or my imaginary part divided by r, where again, r is the absolute value of my complex number, right? Then what does this tell me? This tells me that b is equal to r sine of theta. Okay, guys, so here's where we get our trigonometric form. So notice I have a now and I have b. So I can rewrite a plus bi, right, as what is a? It's r cosine theta. What is b? It's r sine theta. And then I have this times I. I'm going to put little parentheses here to really stress that I'm not taking the sine of theta I, right? I have the r sine theta times I. That's my a and that's my b. And I'm just going to rearrange this a little bit to make it look at like we normally do. So here's my definition for the trigonometric form for a complex number. Notice r is common to both terms, so I'm going to factor an r out, and I will be left with cosine theta plus, then I'm going to bring my I in front just to really stress that I don't have, the I isn't, I'm not taking the sine of I. Isn't this cool? Where, what is r equal to? R is equal to the absolute value, right? The square root of a squared plus b squared. This is it, guys. This is the definition of a complex number. Oh, whoa, sorry about that. In a trigonometric form. Was that kind of weird? I bet that looked weird. This is it. So again, let's write that again. This is a plus bi is equal to r times cosine theta plus I sine theta. And if you kind of think of that a plus bi as kind of like an ordered pair, a comma b, this kind of makes sense, right? Because we know cosine are my x values in the unit circle. We know sine are my y values. So it makes sense that the a corresponds to cosine and that the b corresponds to sine. So that's really the gist of the whole thing. That's going to be my form. One other thing I just want to point out, and let's maybe put this in with our, sorry, I should have done this before. Put this in with our definition. Also, we have where r is equal to the square root of a squared plus b squared. And I know this isn't a huge deal, but this is what's going to help us when we go from complex form to trig form. And what would tangent of theta be? It'd be b over a. So that's just one thing that you want to kind of tuck away in the back of your mind, is that tangent of theta is equal to b over a. So let's do some of these. I'm going to keep that up there. All right, so remember the trig form. And a lot of times this is what I'll do. I'll just, now this is kind of bugging me. All right, so a lot of times what I'll do is I'll just write down something, especially something that I know I need to memorize. I might write that down a couple of times just so I start rim of a complex number. So I know that a plus bi, what does that equal to? R times cosine of theta plus I sine of theta, okay? R times cosine of theta plus I sine of theta, where R is the absolute value of that complex number. So the square root of a squared plus b squared. So for a couple examples. Let's find the trig notation. Find, whoa, people, what just happened to my find? I was looking at my notes while I was writing. Shouldn't do that. Find the trigonometric or the trig notation for the complex number, or the trig form for the complex number. Okay, so let's start off with A. So let's just start off. Let's have some fun here. So let's let I'm gonna look at my complex number be -2 minus 2 root 3 times I. Okay, so what I like to do with this is sometimes it's hard to memorize things, right? So what I do is I do a quick sketch of this. So I'm going to go -2, -2 roots. So I know this number is right about here, right? And I know a couple things here. I know this is going to be my theta right here. And I know that this is my point right here. And what else do I know? I know that this distance here is a -2 root 3. And I know that this distance here is a -2, or just 2, right? So if I want to find the complex form or the trig form, what do I need to find? We need, right, if I look at these, what do I not know here? What do I need? I need r and I need theta, right? So r is going to be fairly simple to find. R is the square root of -2 squared plus a -2 root 3 squared. So what do we have here? That's going to be the square root of, that's 4. What happens when I square this? Well, I just multiply it times itself. So -2 times -2 is 4. Root 3 times root 3 is 3, right? So 4 times 3 is 12. So look at what I get. I get the square root of 16, which is also known as 4. Okay, so this is good. So I know that r is 4, right? That's pretty cool. And now to find theta, there are a couple ways that you can find theta. So we know that the relationship tangent of theta, right, is equal. So now listen, you can use tangent, you can use cosine, or you can use sine. You just need to figure out what theta is. So I think your book uses cosine. So we can use cosine. We don't have to use the tangent, but I've seen other books use tangent. So what do I know? I know that cosine, remember, of theta. Now you can go back to here and you can remember that cosine is a over r, or I could just look at the triangle that I've created, right? I know that this is 4. So what do I know the cosine is? I know cosine is x, so that would be -2 over my r, which is 4. So I want to find an angle, right, in the third quadrant whose cosine is a -1/2. So what's my reference angle going to be? My reference angle is going to be 60 degrees, right? Because I know that the cosine of 60 degrees is 1/2. So I know that needs to be negative though, so I'm going to have pi plus 60 degrees, or pi over 3 if I'm going to go in radians here. So what is theta going to be? Theta must be pi plus pi over 3, or a pi over 3 away from 3 pi over 3. So theta must be 4 pi over 3. Okay, so what is the form for my trig, or what is the trigonometric form then? Well, what is r? I know r is 4 times cosine of theta, which is just cosine of 4 pi over 3, plus I times sine of 4 pi over 3. And you guys are done. That's it. All done. That is the trig form for your complex number, -2 minus 2 root 3. Isn't that cool? So you don't simplify this or anything. If you did simplify this, if you actually took the cosine of 4 pi over 3 and took the sine of 4 pi over 3, guess what you're going to get? Just guess. You're going to get this, right? These two are equivalent. They equal exactly the same thing. Okay. Now remember, these numbers aren't unique. There are a lot of angles that are coterminal with 4 pi over 3, but in general, we usually pick an angle that is between 0 and 2 pi. Okay, but you could pick this angle here and put a -2 pi over 3, or you could go around another 2 pi, right, and pick another angle. But in general, we do that. And can we list this in degrees? Of course we can list it in degrees. Also, I'll be very clear on which one I want, but we could have cosine 4 times the cosine of, well, 180 plus 60 is what, 240? So 240 degrees. And that's the trig form of my complex number. Let's do one more, because I don't know about you, but I had a great time. Let's do one more. So B, let's see, what one do I want to do though? Let's look at, how about 1 minus I? This is a good one. So, and I'll show you with the tangent thing. So anyway, I'll show you with the tangent thing if you want. You might just see this if you go and look for, I don't know why you would ever go and look for videos other than mine. But if you do go and look for videos other than mine, sometimes you'll see them use tangent. So again, what do I need? I need an r and I need a theta, right? R I know is going to be the square root of a plus a squared plus b squared. So I get 1 plus 1, which is 2. So if I look at the graph of this, and I really recommend looking at the graph of it, this is over 1, down 1. So I know, right, that I need an angle. This is going to be my theta here. Okay. So let's look at, and let me tell you about the tangent thing. So tangent, and if I look at kind of this is -1 here, this is 1, this is root 2. One way you can look at this is if I did look at tangent of theta is y over x, right? So if I took y divided by x, I see that the tangent of theta is -1. Or if I had done, you know, cosine, I would have seen that the cosine of theta is 1 over root 2. Guys, these are all going to give us the same thetas. So what is my reference angle going to be? Well, I know when I take the tangent of pi over 4, right? Tangent of pi over 4 is 1. So I need an angle in the fourth quadrant whose reference angle is pi over 4. So if this is 2 pi is the same thing as 8 pi over 4, right? Then what does this imply? This implies that theta then is 7 pi over 4. Or in degrees, because pi over 4 is 45 degrees, that's 315 degrees. Okay, so what is my number equal to? 1 minus I is equal to r, which is the square root of 2, all times the cosine of 7 pi over 4 plus I sine of 7 pi over 4. Again, that's assuming we're taking an angle between 0 and 2 pi. Or if we were in degrees, that would be root 2 times the cosine of 315 degrees plus I times the sine of 315 degrees. That's a good time. That's a good time right there. I know you're probably asking, but Sarah, what about the other way? I understand. I would be asking the same thing. So we looked at going from a standard form. When I say standard form, I mean standard form of a complex number. What if we were given a trig form, right, and we want to find the standard form? This way it's a little bit easier. Find the standard form. I hope that made sense going to trig form. If you need more examples, please just, you know, send me an email, let me know, and I can make more examples. Don't you worry. I love doing these. So let's write the complex number in standard form. And let's start with something pretty simple. Let's look at well, I don't know if this is pretty simple, but root 8 cosine of, and I don't know, just for something, I say for sometimes. Do you guys say for instead of for? Just for something different, let's look at standard. Let's look at degrees first. So how about cosine of 300 degrees plus I? Now this must be the same. Sine of 300 degrees. Okay, it doesn't make sense for these to be different because it has to be the same for us to be at one number. All right, so this guy is as easy as just actually taking the cosine of 300 and taking the sine of 300. So the cosine of 300 degrees, right? We've been doing this now for a while. 300 degrees is in the fourth quadrant. It has reference angle 60 degrees, right? Cosine of 60 degrees is 1/2, and in the fourth quadrant, cosine is positive. So that's a positive 1/2. Sine of 300 degrees, well, the sine of 60 is root 3 over 2. We're in the fourth quadrant and sine is negative in the fourth quadrant. So this must be a negative root 3 over 2. Okay, so what does this angle become? It becomes root 8 times, what did I get the cosine of 300 to be? 1/2, right? Plus I times a negative root 3 over 2. And now let's simplify this a little bit. So root 8, right, I can rewrite as 4 times 2. What's the square root of 4? Last time I checked it was 2. So root 8 can be rewritten as 2 root 2. all times 1/2 plus, no, let's go to minus because of that negative, minus root 3 over 2i. And now let's take that through, and what do we get? We get root 2, right? If I take this through here, my 2's cancel. If I take it through here, my 2 also cancels. So I get root 2 minus, what would this be? Root 6i, or I root 6. Sometimes we'll put that I in front just so it's clear that that I does not go underneath the square root. So I hope that makes sense. Let's do one more of those, and then I think I'm going to, we have a little bit more to get through. So we need to talk about multiplication and division, and then a theorem. So I think I'll break this lecture up into kind of 2 parts. So this will be my first part, and then let's do one more example, and then we'll do, let's do one more example of turning it from trig to complex. And then we'll call it good. So what if we had something where we had, I'm interested, I should figure this out before. How about, sometimes I try and come up with these in my mind, and that's not always a good thing. How about 6? No, I don't want to do 6. Oh, this one will be interesting. Let's look at 8 times the cosine of pi over 2 plus I sine of pi over 2. So this one will be pretty, I think you'll see it's pretty simple. So cosine of pi over 2, right, that's on the y-axis, and cosine are my y values, or x values. So cosine of pi over 2 is 0. Sine of pi over 2 is 1. So what does this equal? Then this equals 8 times 0 plus I times 1. That one's really cool. So look at what we get. We just get 8i. Right? Because 8 times 0 is 0. Now, why is that true? So look at this. Let's see 8i. Where would I graph 8i? I would come up on the imaginary axis, and that would be it. That's my number right there. That is 8i, right? And think about that. What is this angle right here? Sure enough, that's pi over 2, right? And I'm only going, and what is this distance? What is the absolute value of this number? It's absolutely 8. So that makes sense that I should just get 8i for the number 8 times cosine pi over 2 plus I sine pi over 2. All right, guys, I think I'm going to stop this for now. We have quite a bit more to get through, and we're almost at a half hour already. So try those, work on converting those from trig to standard and vice versa. Let me know if you have any questions, and stay tuned for the next part.